Okay, so we're going to pick up here talking about chapter 2. As we talked about last time, we got to the idea of taking measurements. And remember that when we do take measurements, it's really important to always look at the actual piece of equipment that you're using and try to figure out really two things. Sort of one is, what is the scale that's the big numbers that are on it, and what does the little markings really represent. That way you can figure out really how far you can take your reading. Remember that you can pretty much take your reading in most cases to one more place than the smallest marking. Not 100% of the time, but in a lot of cases you can do that. When we do take a measurement, as we talked about last time, remember that we want to always record what we sometimes refer to as all the certain numbers. So those are numbers that pretty much no matter who takes a look at it, everybody really should agree that it's at least that much. But then we also want to record what's sometimes referred to as the first uncertain number. That is basically the number where there might be some disagreement. I may look at it and go, it's like halfway there. Somebody else may think it's just past the mark or something like that. And that's the first uncertain number. That really is where sort of the uncertainty, the error, if you will, in the measurement sort of lies. When we record all the certain numbers plus that first uncertain number, that's basically what is referred to as significant figures. So that's basically how we get our significant figures. As we talked about last time, we also want to never sort of cut off a number. And what I mean by that is, again, if you hit something that's like dead on a number and you have the ability to go to, say, 2 decimal places, you should record that second decimal place as a 0 to maintain the significant figures. Again, I think we looked at a number like 1.4 versus 1.40. There's a big difference in terms of what those values mean when you record it, and really the uncertainty associated with those values. Any questions on any of that stuff there we talked about last time? Okay, so I think we laid up right here. So let's take a look at this one here just to do a couple more sort of examples of recording our measurements. This again is a liquid that's in a glass container. So as we talked about last time, there is going to be a sort of curvature of that liquid, which is the meniscus. And you always want to read from the very badly drawn there, bottom of the meniscus. When we look at this, we see that this is 30, that is 40, and we actually, so when we look at, whoops, before I go back. So when we look at this guy, that is 30, that is 40. And there really is, we start counting here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 40 coming there. So in this particular case, each marking represents 1 milliliter, the smallest markings. Obviously, the biggest markings represent 10, right, as we go through. Again, looking from the sort of the bottom of the meniscus, everybody should agree it is at least here, which is 35. This marking right here is 36. So we can see it's at least 36, which is obviously why we would record, as we saw on the last page there, 36. Now we see that right here is 37. And obviously it's not right at that line. So it's somewhere in between. And that's where we do make the estimate. So here again, you would want to sort of figure out, does it feel, like half? Maybe in this case, it feels a little more. It looked like they went a little bit more than half on the previous one. And that is how they got to 36.8 milliliters. Looking at it in their opinion, when they came up with the thing, they felt it was obviously closer to the 37 mark, obviously, than halfway between them. And that, remember, is our certain numbers, which means in this particular case, this number does have 3 significant figures. Yeah. Any questions on that? Yeah. What's that? Do you need to know why it curves? Is that what you're asking? Yeah, so pretty much all liquids will have some type of meniscus that will occur, and we'll actually touch upon it sort of later on in a later chapter. But what's really happening here is there is when you have the liquid in there, there's actually a much stronger attraction in this case up to the liquid to the glass. So you get the sides of it sort of rising up, and that's what causes the curvature of the liquid. And in most cases, most liquids will have a meniscus that will sort of look like a U, like that. There actually is some liquids that are actually more attracted to themselves than something like the glass. Mercury is an example of that. If you have something like mercury, it actually does the opposite when it's in a glass container. The mercury is actually more attracted to itself, so it kind of comes in on itself. And something like mercury actually has a meniscus that goes kind of upside down. And so it's actually an attraction. It's the attractive forces between the liquid and the container is what causes that. And if the attractive force is greater between the liquid and the container, you get the typical kind of U-shaped meniscus. If it's not, then you get more of a upside down U sort of shape. That's really why it happens. But regardless of which way the meniscus goes, and I would say probably 99 times out of 100 is going to do the U. You should always read from the bottom of the meniscus. It's always where you should try to take your reading to always get yourself sort of at that eye level to sort of take the reading that way. If you had something like mercury, which actually went upside down, you would actually do from the top of the meniscus in this case, because that's really where the liquid level is. We just see it kind of going down or up because of that attraction, but really the level of the liquid is that middle part, which is why we kind of read from the bottom meniscus. Yes, so always, in most cases, it will be that U, so you want to kind of do the bottom of the meniscus. Occasionally, you won't really see it too much because they've taken mercury out of pretty much all chemistry labs. They used to have barometers that had mercury that you kind of see that upside down sort of move, but most everybody you'll see will typically be that U. Again, sometimes it's a lot easier to see depending on the glassware. If you get a beaker, sometimes a big beaker is sort of hard to see because it's really spread out. But you know, sometimes in a graduated cylinder, you can definitely see it, but sometimes it becomes harder. Other questions? We also talked about this, which again, you will see sometimes. You don't have to include them in most measurements, but just in case you're asked sort of the precision of the device, the way we get that is by taking the smallest division and dividing by 2. So the smallest division was 1 milliliter divided by 2. Again, that's how we get sort of our plus or minus the scale. Again, when we look at something like 36.8, it's basically telling us, you know, it could be somewhere like 36.9, which if you look at the pictures, you know, in the ballpark of where it's at. Again, here, if you decided, you know, it's not really important to record all those numbers, record 36 milliliters like we talked about last time. This now would have only 2 significant figures, which means you're saying the error here is in this number, right? That would then be your estimated digit, which as we talked about, sort of like an example last time, you could say it would be like 37 or 35, which clearly looking at this, 35 is way down here, right? And so it's nowhere near 35. So by killing that last digit and not taking into the proper number of digits, you're making a really crappy measurement and making your error a lot higher than it should be based on your equipment. So always, again, maintain that digits that you could take the reading to. Even if you need to put a 0 to maintain it, it's really important to do so. Any questions on that there? Okay. This is actually a burette, which we'll actually use as well this semester. And it's a little bit different, so I'm just going to kind of look at the blown up picture there. It actually increases as you go down. So up here is actually 0 milliliters. And on the bottom, it actually increases. So when we have something like a burette, and that's because basically the liquid comes out down here. So it drops, comes out the bottom. So when we fill it to the top, it is 0. Typically, when we use a burette, it's usually a couple decimal places is usually where you give the answer to. And the reason for that is we can look here again. This is 28. That is obviously 29, which means the biggest markings here is 1 milliliter. Our smallest markings, if we count starting here, is actually 10 markings going down to the 29. So the smallest markings here represent 0.1 milliliters, which means right here would be 28.1, 28.2, and so forth. Obviously, that would be 28.5. So when we get down here, we can see it's at least 28.5, 28.6, 28.7, 28.8. I'll learn how to count. And about 29 is here. Again, the bottom of the meniscus is in that area. So as we can see, we would take a reading of probably like 28 point, everybody would agree it's at least 6, 7, 8, at least 28.8. Again, it's not exactly right at the 28.9, right? Not exactly at the 28.8. We can go to 0.1 as the smallest marking, which means typically speaking, we can take a reading one more place to the right of that. And as they hopefully have there, we'll see what they ended up with, but probably something like 28.85 maybe. I'll go back here. There we go. Oops. 28.85. Again here, these would be our certain numbers. As we saw with the zoomed up one, we could see all the way down to the 28.8. It wasn't exactly there. It wasn't exactly 28.9. This being our first uncertain number. This one now would then have 4 significant figures here. All these guys here would be significant. Any questions on that there? Again, we get this plus or minus by taking our smallest digit divided by 2. And that again is how we get to there. Any questions on that there? So really, really important, as you can see, and as we talked about last time, you know, the scales aren't always the same on every piece of equipment that you grab. You want to make sure you always look at it. The 2 really main things you want to look at is, as we saw here, markings, what the small markings represent, and really how far you can take that reading to. So why don't you take a second here and see which one you think on this. Again, it is starting at 0, increasing as you go down. This, I think I got a bigger sort of blown up picture of it. We got 20, we got 30, and there is 10 markings here in between. So the biggest markings represent, in this case, 10 milliliters. The smallest markings represents, in this case, since there's 10 markings, actually 1 milliliter. So this big guy here would be 25, right? And obviously this would be 30. We go from the bottom of the meniscus. It's a little hard to see, but I'm going to say it's like right on that second dash. So I believe we would record 22 as definitely being sort of certain. But because the smallest marking here is 1 milliliter, means that we could go one more place to the right, which means we could really take the reading to the first decimal place there. In this case, it looks like it's dead on the line. So this again is a case where we do want to maintain the proper number of digits here and record a 0. That tells us that this number has how many significant figures? It has 3 significant figures. The uncertainty, which where we see means it could be something like 22.1, maybe it's like 21.9, which if we look at the picture, that's pretty reasonable as to where it's at. Again, if we just laid up 22 as our number, this again would say that this 2 would be the uncertain number, telling us it could be like 23 or 21, which clearly is really not near any of those numbers. So it's a very common mistake that people make, that they, you know, try to, it's like on the line, just record the number, but you really got to make sure you maintain those digits so you're not making your measurement really, really worse. Questions on that there? Questions in general on taking measurements? Okay. Yeah. Yeah. Right. Yeah, so in general, not 100% of the time, but almost like 99% of the time, if you can figure out what the smallest markings represent on a piece of equipment, it's almost a safe bet that you could take the reading to one more place to the right. is not 100% proof. I think I did an example the other day where it was only 5 markings and they went by 2s, right? And there's like, 12, 14, 16. So obviously in a situation like that we talked about the other day, where if you look at the markings, say there's 10 milliliters between 5 markings, and you end up, like, let's go back here. If we had our, say that was 10, that was 20. And as we talked about last time, that's like 12, 14, 15, 16, I learned to count, and 18. So obviously, if we fell between the 12 and 14 mark, because of this particular scale, the real place between 12 and 14 would have to be 13. In this case, you would have to give it sort of just 13, nothing else, because there's not enough room between the 12 and 14 to figure out where does 12 stop and where does 13 begin. Between that, there's just too much numbers in between. So that's a rare exception. I would say, again, 99 times out of 100, you could go to that smallest marking, go one more place to the right, and you should be good. Yeah. Other questions? Yeah. Yeah, so the triple beam balance, like the ones we were using the other day, really the one you should look at is probably the smallest sort of beam, if you will, the one that was, I think, in front. It was like ones, right? It was like 1, 2, 3 places. And you would want to look at that kind of like a ruler, how many markings were between them. And, if there was 10 markings, that means each of those ones is like 0.1, which then means you should be able to take it one more place to the end. And you would add in all the other numbers if you had the bigger numbers in front of it. But really, to figure out how far you could take it, you would want to look at that smallest sort of markings, which would be found on the third sort of beam, the smallest markings. Okay. You would want to look at it and figure out, what is the smallest markings on that one is, and then go probably one more place to the right. Other questions? If I remember off those, I think there's 10 markings between 1 and 2, for example. So that means each one's 0.1, which means you could technically kind of go one more place to the right, probably. Other questions? All right, so we talked about taking proper measurements. There's really a significant figure. So here we're going to talk about how to count significant figures and numbers. So let's talk about these different ones here. First off, when we're counting significant figures, pretty much anything that is a non-zero is significant. When we're counting significant figures, we always start counting on the left, and we always start counting when we hit the very first significant, very first non-zero. So in this particular case, we would start counting at 1. So 1, 2, 5, 9, they're all non-zeros. They would all be significant. There are zeros is sort of the next big category for significant figures. And there's 3 different types of zeros. There are ones that are sometimes referred to as leading zeros. Those are zeros that come before your very first non-zero number. They are not significant. So in this particular case, none of these zeros here are significant. We would not start counting until we hit our very first non-zero number, which is 4. And then obviously the 9 after that, which would then give us 2 significant figures in this particular case. There are zeros that we find sort of trapped between 2 non-zero numbers, and those are significant. So in this case, starting on the left, we would start counting here at the 5, which is our very first non-zero number. The 2 zeros here are significant, and then we would end up obviously with the 4 at the end. So in this particular case, all 4 of those guys are significant, and this guy would have 4 significant figures. Now, I would say probably the last zero that really gives people the sort of the hardest time is the zeros that come at the end. And the zeros that come at the end, sometimes referred to as trailing zeros, they could be significant or they may not be significant. And what determines whether or not they are significant or not is there a decimal point in the number? So it's very important to know this. The decimal point does not need to be near the zeros at the end. They just need to have a decimal point in the number. So if there is a decimal point in the number, any zero that comes at the end will be significant. If there is no decimal point in the number, then the zeros at the end would not be significant. So if I wrote 600 like this, there is no decimal point in this number as it's written, which means the 6 here is the only significant figure, and it would have one significant figure in this case. Now, if I wrote this guy the same way with the 600 and a decimal point at the end, we would start counting here at the 6 with the decimal point. All these numbers, all the zeros at the end are significant, and it would have 3 significant figures in this particular case. So yeah. Yeah, so if you're asking something like 600.00, something like that, or yeah. So again, we do the same thing. We would go, that is significant. These are all zeros now that come at the end. There's no other non-zeros after that, right? We would see a decimal point there, which makes every single one of these significant. Yeah, so they would all be significant. So what I got there, 6, looks like in this particular case. Other questions on that? You know, if I had something like 0.00100500040, how many significant figures would that have? It's a good answer. I don't know. I just wrote it. Let me see. Let's take a look. So starting here, if we were to dissect this, all these zeros here are not significant, even though those zeros that come after a decimal point, they're not significant because of we are not starting to count until we get to here. That is our very first non-zero number, and that is where we want to start counting. We then have some zeros that are trapped, which means they're significant. So that's 1, 2, 3, 4. More trapped zeros, 5, 6, 7. And now we have this 0 at the end. Is it significant? The answer is yes, it is, because there is a decimal point right there. So again, the decimal point doesn't need to be right next to the 0. It just needs to be in the number for it to be significant. So I think you're correct there. Was that 8 we got there, I think? Any questions on that there? And then there is obviously a difference, right, in the meaning of these numbers. You know, when we do something like 600 versus 600 with the decimal, the error, the uncertain number in this guy is actually the first digit, right? Which is the one and only significant figure in this case, which means we're talking about like a range of error, if you will. Like this could be like 700 versus like 500, maybe on the low end. With this being the third significant figure where the uncertainty lies, we're looking at a range of error, maybe like 601 to like 599, right? Much better measurement, right, than the one above with the one significant figure, less room for error and stuff like that. So there really is, you know, a difference in how you write numbers as to really what they mean in terms of measurements and how good they are. Any questions on that? Yeah. Yeah, so again, it would depend on your graduate cylinder. You would want to look at it like we kind of did in the previous examples and figure out, you know, really how far you could take it. You know, if that 50 was in a graduated cylinder where the smallest markings were 1 milliliter, right, then you could take it to, you know, 50.0. Yeah. Yeah, so it would depend on that. You would probably, in most cases, probably add the 0, to be honest with you. If you had like, if you're asking, would you write 50 point and not like 50.0? Probably in most glassware that you would use, it probably would be like, you would be able to go to that extra decimal point. But yeah, in those cases. So I would refer to you that back to what we've been talking about. You just want to make sure, you know, you figure it out for the particular piece of equipment. The other thing where we talked about with significant figures, it's important to remember is a couple of things. The uncertain digit, or sometimes what's referred to as the estimated digit, is not necessarily always the last digit, as we see here, right? So the 600 with no decimal, the estimated digit is actually the first number, right? The 600 with the decimal point, the estimated digit is like the third number, the last number. Again, 9 times out of 10 is probably the last digit, but not always the last digit. So if you're ever asked, what is the estimated digit? What's the uncertain digit? It should always be the last significant figure. So that's a good way to remember it. The last significant figure, which might not always be the actual last number in the actual value. Questions on that? The thing I was just going to say is remember that sometimes the only way to give an answer to the correct number of significant figures is to write it in scientific notation. So as we talked about last time, when you write a number in scientific notation, all of the numbers that come before the times 10 part are always significant. So sometimes the only way to kind of hit it to the right number of significant figures is to actually write the number in scientific notation, because you could kind of control how many significant figures you write. You know, for example, if you wrote, you know, if I wrote 1.2 times 10 to the 3 versus 1.20 times 10 to the 3 versus 1.200 times 10 to the 3, this number has 2 significant figures, right? But if I needed 3, I could write it like that, right? Which would then have 3 significant figures. Or if I needed something like that, you know, it would have 4 significant figures. So sometimes if you need to get something to the right number of significant figures, and there's no way to do it sort of in, sometimes referred to just decimal form, if you will, you could write in scientific notation, because you could really control how many significant figures that you want to write. Any questions on that? Yeah. So when you write it in scientific notation, it is just the, I'm gonna pass the roll sheet around, so make sure you sign. It's always just the numbers before the times 10 part is always the significant ones. So that sometimes is where people run into trouble too, when they're maybe asked a question like this, like 1.2 times 10 to the 3. They might convert it into like a decimal and move to decimal places and go, I got some zeros and all that. And then they'll start counting those things and stuff like that. But it's always based off of how it's written in scientific notation and those numbers that come in front. Should be other questions on that. Now, the last type of number is what is referred to as an exact number. And exact numbers are pretty much 2 things. They are things that are counted. You know, so if I had like pens on my desk here, I'm not going to do some type of experiment to figure out how many pens I have. I'm just going to simply count how many pens I have. So there are things that are counted. The other place that we commonly see definitions, I'm sorry, our exact numbers are in definitions. Like 1 or 12 inches equals 1 foot, right? 1 inch equals 2.54 centimeters. These are considered exact numbers. And what that means is, as we're talking about next, when you do calculations, you don't have to worry about the significant figures in those type of numbers. They can have pretty much unlimited significant figures, which means we sort of ignore them. Now, if you remember, we talked about 2 different types of units. We talked about English units, like what we use, inches and feet. We talked about metric units. And we talked about that you can cross over, obviously, between English and metric units. And that is the one sort of definition that you should look at the significant figures. So if you do a crossover, you know, for example, I don't know, 1 pound equals 453.6 grams, right? This is technically English to metric sort of conversion factor. Technically speaking, the rule is you should look at the significant figures in this number when you're trying to decide how many you should end up with in the calculation. And obviously it would have 4. So that is really the sort of the correct way to do it. 1 inch equals 2.54 centimeters. You don't have to worry about that because that's an exact sort of conversion. But any sort of one where you cross from English to metric sort of conversions, you technically should look at it. The good news is, as we'll talk about here in a second, pretty much in most cases, if you're doing a problem, most of the time, and it's just a conversion problem or something like that, the number of significant figures you should end up with is kind of like the same number you start with in most cases, not always, but in a lot of cases. So let's talk a little bit about that, I think. So let's take a look here real quick before we do that, I guess. There we go. All right, so take a second here, figure out how many significant figures we got in each of these. take a look and see. So starting here in the first one, we got all these zeros that are not significant. We're going to start counting right here at the 3. The 0 is trapped, so this should have 3 significant figures. Any questions on that one? This is scientific notation, which means simply we just need to look here before the times 10. And that means all these numbers are significant. 0 at the end is not a problem because there is a decimal point there. So that is 4 significant figures on that one. Here we got all 3 are significant. So we got 1, 2, 3 significant figures. Here we start counting at the 1. We have a 0 here that's at the end, no decimal point written. So this actually would have 1 significant figure in this case. And lastly, start counting here, not significant. That 9 is really where we should start counting in this number. We got a trap 0, which is significant. We got a 2, which is significant. This last 0 is significant because there is a decimal point there. And that looks like 4 significant figures. Questions on any of those or how to count significant figures? Reminder as well that your calculator does not always spit you the answer, right? And the correct number of significant figures, you need to convert them to the right sig figs and all that good stuff. All right. Let's skip this one, I think. Let's talk a little bit about rounding real quick, just to make sure, you know, you can do the normal rounding rules. If it's less than 5, you're just going to kind of drop the rest of the numbers. If it's sort of more than 5, then obviously you will look and round up by 1. You never want to do any sort of extreme rounding. So for example, if I had 13,333 and I run around to 2 significant figures, what should the answer be? Yes, sir. Sounds good. 13,000. Anybody for 13 without the decimal point? I like it. So what about 13? So let's talk a little bit about both of these numbers here. 13 is definitely 2 significant figures, right? So you definitely got 2 significant figures, which is a common sort of answer sometimes people will give for this one. But there is a big difference, right? If I owed you $13,333 and I said, hey, here's your 2 significant figures, here's 13 bucks. I'm probably not going to make it out the door, I imagine, right? That is a very big difference in the meaning of the number between 13 and 13,333, which means although it is 2 significant figures, we never want to change the actual meaning of the number or the value. 13,000, as was said, without the decimal point is correct. It has 2 significant figures as these zeros are not significant. And, you know, it's roughly the same value. You know, maybe if I owed you $13,333, it said here's $13,000. I get like the $333 teacher discount, right? You know, maybe I'm okay, you know, but it's relatively the same value. So it's a very common thing that people will do is in the effort to get the right number of significant figures, they do what I call extreme rounding, and they just chop off numbers to get it to the right one. So you want to make sure that you round the number correctly, but you also want to make sure you don't change the meaning of it in an effort to get the right number of significant figures. Any questions on that there? In this particular case, it just happened to be I asked for 2 significant figures, so that's where we would round to, if that's what you're asking. You wouldn't want to write 13 because, again, 13 represents a very different numerical value, right, than 13,000. So you don't want to do that. So you do, in this case, need to maintain the zeros at the end to maintain really the value of it as 13,000, which is basically the same. And you, as was said, it should not have a decimal point, as was mentioned earlier. If we did 13,000 with a decimal point, that would then have how many significant figures? It would then have 5 significant figures, as these are significant. These are the zeros at the end, which are significant because of the decimal point there. And that would be too many significant figures in what we were going for. Question on that? Okay. So again, we would not want to do that, as that would be 5 sig figs. All right, so just don't go crazy on the rounding. Yeah, don't, change too much of it. So here, if we want to round this to 2 significant figures, that would take us to the 5. We would look here, which is more than 5 to 7, and we should end up with 36 meters. Going to 2 significant figures, again, would take us to the 8. We would look at the next digit, which is the 2, and it's less than, so we would just drop it, and here we would go with 3,800 grams. Again, no decimal point here, otherwise it would then be 4 significant figures. Here, looking here, our second significant figure is actually right there at the 6, as those zeros at the beginning are not significant. And that means that we would end up with 0.0026 liters. By the way, always a good idea to keep the 0 before the decimal point so numbers don't run together. So it's a good idea to put that in there. And lastly, here we would look at the 2, which obviously the 8 is what we would look at to determine what we should do. We should obviously round up in this case to 1.3 kilograms. Any questions on those there? Question on counting sig figs or anything like that? Yeah. Then more importantly, let's talk about what we should do with significant figures when we're doing calculations. So whenever you do calculations, you should always try to give the answer to the correct number of significant figures. There's really 2 big classes of stuff that we do. One is we multiply or divide. So when we multiply or divide, the answer that you end up with should have the same significant figures as whatever number had the least number of significant figures. So multiplying or dividing, we look at significant figures, and whichever one is the smallest number of significant figures, which basically means that's your worst measurement, is how many significant figures your answer should have. So for example, if I had 2.55 times 1.3, if I did that there, try this calculator here, 2.55, 1.3. On my calculator, I think I get, can't read it, but I think it says something like that. So when we look at it, we are multiplying. This guy has 3 significant figures. This guy has 2 significant figures, which means my answer here should end up with 2 significant figures, the same as the smallest number, which means I would want to take this guy and give an answer of 3.3. Yeah. Question on that there? Same thing with dividing. Again, least number of significant figures is what you should go with. Now, for addition and subtraction, we look at not significant figures, but we look at decimal places. And it's the same thing. It is the one with the smallest number of decimal places is the decimal places you should take your answer to. So whichever one has the smallest number of decimal places would be your worst measurement, and that is how far you can take the reading to. So for example, if I had 1.25 plus 3.2 plus 1.00, do some math here without the calculator. Looks like a 4, 3, 4, 5. There we go. We were looking at decimal places. This guy has 2. This guy has 1. This guy has 2 decimal places, which means the smallest number of decimal places is the first decimal place, which means we should take this right there and end up with 5.4, which would have, thank you very much. It is a 5. Thank you. It would be 5.5. That is correct. Thank you. Make sure you look at this number as well. That would be good. So it should be 5.5, which has 1 decimal place. It's important when you look at it, it does have 1 decimal place, but 5.5 has how many significant figures? It has 2 significant figures. So keep that in mind when you're talking about sig figs or decimal places. Any questions on that there? Now, what happens if we have a lot of stuff going on, like we're combining things, right? So, so let's try. So let's say we had 3.25 times 1.2 divided by 4,444. So if we're doing some type of complicated sort of calculation, typically we would do what's in the parentheses first, which means we're multiplying in the parentheses. So multiplying, we should look at significant figures, which means if we technically got a number for the top, this guy has 3 significant figures. This guy has 2 significant figures, which means the answer for the top part should end up with 2 significant figures for the top. Yes, sir. Yeah, we're going to talk about that in just 1 second. So if we get the answer there on top, which technically should be 2.2 significant figures, we then would be dividing that 2 significant figures by 4 significant figures on the bottom, which means ultimately our answer should end up with 2 significant figures. So if you're doing multiple steps, you need to keep track of the significant figures as you're going through it. And based on sort of the last sort of step that you do, that's really how you can determine what your answer should be. Now, the question is, what about rounding? And the answer is, it's a really good practice in most problems that you do not to round a lot until the very end. So you should keep track of all your significant figures and all that and what you're doing and really clean it up at the end. The reason for that is if you go strictly by significant figures and you're doing multiple step calculation, you like round this guy here, take that answer, get an answer, round it again, take it, do another step, round it again. Every time you round along the way in that calculation, you're going to find yourself farther and farther away from probably the right answer. So it's a really good idea to keep a good amount of digits if you're doing multiple steps, like even in your calculator. Personally, when I do it in a calculator, I keep like the whole number and just continue on with the calculation. And keep in mind where you should end up in terms of significant figures and clean it up at the end. Otherwise, again, if you do a lot of really strict rounding, especially in a problem where you're doing a lot of steps, when you get to the end and you look at the answer, you may find yourself pretty far away. So general rule is not to round too much until the very end, but you should keep track of what you're doing and figure out where you should end in terms of significant figures. Other questions? All right, so if we look at these guys here, let's just run through them and see what we should end up with. Here we are multiplying. Again, the calculator does not always give you the proper number of significant figures. This is 3 significant figures. That is 2 significant figures. Again, we're multiplying, so that's what we should be looking at, which means we do want to end up here, and I won't screw it up hopefully this time, but that is a 7 next to it, which means we should end up at 9.4 as our answer. 2 significant figures based on the one with the smallest. Here we're dividing, so again, significant figures is what we're looking at. That is 4 significant figures. That is 3 significant figures, which means we should end up with 3 significant figures. Remember that we're not going to start counting until we hit the 7. That means that's the second, that's the third significant figure. That's a 2, which means we just dropped the rest of it. And we should end up with 0.0758. Again, 3 significant figures in that case. Any question on those 2? Here we're adding. So when we're adding, we are looking not at significant figures, but we're looking at decimal places. So that is 2 decimal places. That is 1 decimal place. That's 3 decimal places, which means we should end up at 1 decimal place, which takes us to the 29.1. And that is actually what we should have. That 29.1 has 1 decimal place, but how many significant figures? Yes, 3 significant figures. So again, those are 2 different questions and things. You want to keep that in mind. Here we're subtracting. So again, decimal places, 4 decimal places, 1 decimal place, which means our answer should end up actually at 1 decimal place. That is an 8. So that looks like 0.6 would be our answer there. Any questions on that? What happens if I'm adding a number that is a whole number with something that is a decimal? I end up with 124.5. I should take this to the smallest number of decimal places is no decimal places, right? So I should take this to 124. Yes. Yes, you are right. I need to watch that second number. Thank you very much. 125. It's my first day. What are you going to do? I don't know. Thank you. Yeah, but it should be a whole number in that particular. Any questions on rounding, significant figures, calculations with significant figures? All right. So we talked about this, I think the other day as well. Remember that we do, use prefixes, and a reminder that, when we look at a prefix and we see something like this, as we talked about, that's how much there is in the base unit to one of the prefix units. So again, if we were doing centi and 1 centimeter, that would be 10 to the minus 2 meters. And that is the correct way to do that. Again, very common. People, as we talked about last time, reverse those. As we talked about scientific notation, that is basically 1 times 10 to the minus 2 if you need to kind of put in your calculator, sort of that way. All right, we talked about some of these length equalities, I think, last time, but these are some common ones. Again, equalities, basically 2 things that represent the same amount. 1 meter is 100 centimeters, 1,000 millimeters in a meter, and 10 millimeters in a centimeter. Some common volume ones that we talked about. Again, we do definitely see this guy a lot, as we talked about. A liter is 1,000 milliliters. And we talked about the cubic centimeter, which is the same as a milliliter. And again, that is one way you could get a volume, as we did, length times width times height. Kind of like what you did in the experiment the other day. Took 3 different sort of length measurements. You can multiply them together, and that would get you your volume. Now, when you multiply them together, they should have the same number of significant figures as the one with the least number of significant figures when you do that. All right. And we talked about that, I think. We'll skip those. Good. All right. I'm just going to kind of skip ahead a little bit since we talked a little about that stuff last time. All right, we're going to get into some conversion factors and doing some dimensional analysis sort of problem. Conversion factor is really just a conversion factor is really just a fraction that we use really to do dimensional analysis in chemistry. So from any equality, 12 inches equals 1 foot. You could write 2 conversion factors where you go 12 inches over 1 foot or 1 foot over 12 inches. And when we do problems in chemistry, we like to sort of do them through what is known as dimensional analysis, which basically shows the units canceling each other out. So for example, if I had 22 feet and I wanted to know, how many inches is that? What I would do is use the conversion factor and basically go opposites cancel when we do dimensional analysis. So we would use the conversion factor over here. We would do a problem, and this is really what is referred to as dimensional analysis. 12 inches on top, 1 foot on the bottom. Although this 22 is not written as a fraction, it really is like a fraction. It's like on top, and opposites cancel. Basically, feet will cancel each other. It's the same idea as when you take 2 divided by 2, it equals 1. If you take feet on top and feet on the bottom, it equals 1. They basically cancel each other out. What we're doing mathematically when we sort of set it up like this is we're multiplying everything on top and coming back and dividing by everything that's on the bottom here. Most of the time you don't write the 1 there on the first guy. So basically what we would do is we would take obviously 22 in this case, we would times it by 12, and it would give us 264 inches. Inches is the only units that are left. Again, the feet will cancel each other out. Now, when we look at something like this, we do want to give it to the right number of significant figures. So when we look at this, this right here is a definition, and it does fall under the exact numbers, which means we don't have to worry about it in terms of significant figures, which means the only number that we have really to worry about is the original number here, which has 2 significant figures. That means that we should give the answer to 2 significant figures, which is there, which is 260 inches would be the correct significant figures. So as I was mentioning just a little bit earlier, when we were talking about exact numbers, this is sort of a English to English conversion, which means it's an exact number. You don't have to worry about it in terms of calculations. Most of the time, a conversion factor that you use will come from an equality that you probably don't have to worry about the significant figures in the conversion factor. And most of the time you could go with the original number as to how many significant figures. The one exception is if we had a conversion factor, again, that came from a crossover of metric to English, then you should look at the significant figures. But if it's metric to metric, if it's English to English, if it's something that's classified as an exact, like 1 inch is exactly 2.54 centimeters, you don't have to worry about the significant figures in the calculation. And probably 9 times out of 10, if you go with the sig figs on the original number, you'll probably be in good shape. Questions on that? You do need to show the calculations similar to my scribble there on the bottom where we see the units canceling. It is what is referred to as dimensional analysis and how they want you to sort of show your calculations. That's pretty much what this big page says here. An equality really is, as we talked about, basically 2 things that are on different scales, but do represent the same amount. If you have 100 pennies, that represents the same amount as you had $1. They represent the same amount of money. If you went through a drive-through, you could pay with pennies, right? You can pay with dollars. They might not let you through the drive-through if you pay with pennies, but you typically can. And we can use it obviously as a conversion factor. You typically do not use the conversion factor, both conversion factors in a problem. Otherwise, you're kind of undoing your work. So you pick whichever one you need for the correct problem. Here are some conversions, again, sort of English to English conversions, which again, you don't have to worry about sig figs. Metric to metric, you really don't have to worry about significant figures. Technically speaking, other than like this one, you technically should look at the significant figures when you're trying to determine what you should end up with. If you're doing a conversion in dimensional analysis, you're basically doing some type of problem like this, where you're taking a unit A to unit B to unit C. And basically, you want to look at each of these and determine whether or not you should look at the significant figures. But even in a calculation like this, probably most of the time, it'll probably end up being this guy's the smallest anyways, in a lot of cases. Again, not 100%, but more times than not, if you go with that original sort of number, you'll probably be okay if all you're doing is just conversions. There are some conversions and stuff that you should know, right? 1 inch is 2.54 centimeters. There are some that won't be given to you. You should hopefully know time, right? There are how many seconds in a minute? 60 minutes in an hour, hours in a day, 24, not 60. Yeah, that's a very common. People make that mistake. Yeah. So, there are some stuff that obviously won't be given to you, some stuff that you should know. I think we went over some of these, but you should know this guy, obviously. You should also know probably this conversion is a common one that we use a lot. And, this guy and this guy. Yeah, for sure. So those, we do come across those a lot. All right. So if we're going to write some conversion factors for an equality, here again are the couple ways you could do it. If we have 5,280 feet in a mile, you could basically write 5,280 feet up on top and 1 mile on the bottom. And you could flip it the other way. Which one do you need to use? Again, depends on obviously, what the problem is asking you for. If you were starting with feet and needed miles, you would use the one on the right in this case. If you were starting with miles but needed to figure out feet, you would obviously use the one on the left here. Again, opposites sort of cancel each other. If you're driving 65 miles per hour, that basically means you are going 65 miles in 1 hour. It's like a rate. And again, you could do it one of two ways. 65 miles over 1 hour, or obviously 1 hour is 65 miles. Again, here, same deal. You would use whichever one you need for the particular problem. If you were going, 70 miles an hour, want to know how long it's going to take you to get somewhere, you would use the one on the right, because you would go, or if you went 70 miles and you want to know how long it would take you, you would use the guy on the right there. 65 miles on the bottom, hour on top, miles cancel, gets you to hours. So again, that is a way you need to set it up so you can see the units canceling. It's a big thing in chemistry to kind of set things up in that approach. Now, if we fill up for 305, see that it was expensive when I wrote this slide years ago, but now, hey, we would probably kill this, fill up for 305 a gallon, I suppose. That basically means obviously 1 gallon of gas would cost you $3.05, or $3.05 would cost you 1 gallon. That used to be like, 91 pricing years ago. Now I don't think you get 87 for that anymore. So yeah, times change, I suppose. Another very common thing that sometimes we need to write conversion factors for in chemistry is percentages. So sometimes we are given sometimes we are given percentages. And really the easiest way to sort of turn a percentage into a usable number is to assume you have 100 of it, right? That basically keeps the numbers the same. Like if you got 50% on your exam, you probably got 50 out of 100. You got 70 on your exam, 70 out of 100. So if you're given something in percent, like we see here, there's 12% body fat per mass. Sometimes that weight is given in kilograms, or mass is given in kilograms. So you could say 12 kilograms of body fat per 100 kilograms of body mass, or you could flip it. Or if you're doing something like pounds, that's the same thing as 12 pounds per 100 pounds of body mass, and you could flip it. So if you're given something in a percentage, you need to kind of convert it into a conversion factor. Definitely assuming 100 is the best way to sort of do that, and the easiest way to do that. So let's talk a little bit about the problem solving and dimensional analysis. Dimensional analysis, as I was just kind of showing you earlier, is the way you're supposed to do most of the calculations in chemistry. It is basically unit-based, which again basically means you have this set up where you show the first unit you're doing, and then you use some type of conversion factor to convert it to another unit. Maybe you're doing multiple ones in a row. And again, here, this is multiplying across the top, and obviously dividing by what's on the bottom here. Here, dividing the unit A by unit A would cancel, unit B by unit B would cancel, leaves you whatever units left there up on top would be your final unit in this particular case. And that's the way you should sort of show your calculations with the units, the conversion factors, things canceling out. Should not just be numbers, that are piled on top of each other, not numbers with units where sometimes people will do like I'm just going to write all the numbers like in this direction and not sure what you should be dividing, what you should be multiplying. So if you set it up like this, you should clearly be able to see what units are canceling, should be able to see what units still stay, what you're multiplying, what you need to divide. You will hopefully not mess up by dividing when you should be multiplying and things like that. So there are general steps to doing dimensional analysis or problem solving. First off, you might want to write what is given to you in the problem. You want to write what you're trying to find. Think about any equalities that are appropriate for it, the conversion factors that go with it. You should set up the problem like I just showed you, where all the units are canceling. You should obviously solve the problem with the proper number of significant figures. Do you need to do every single step there? You don't really need to do like number 5 and number 6 there. Set it up and solve it. If it helps you to write out the conversion factors and all that, you should do it. You don't necessarily have to do it, but you know, it can sometimes help. So there we go. So if we look at a fairly simple one here, obviously we are looking for how many pennies. We're given $3 is what we're starting with. Our conversion factors can be found from our equalities, which is both of these guys. And obviously in this sort of straightforward one, we would want to start with what's given, which is $3. We want to use, in this case, the conversion factor that's on the left, as the dollars are in the opposite location, so they'll cancel. That gives us 100 pennies up on top, $1 on the bottom. Again, here, dollars will cancel. That is going to leave us with pennies, which is what we're looking for. And we will end up with, looks like 300 pennies in this case. Any questions on that there? Significant figure wise, the 100 pennies to $1 is basically an equality. We don't have to worry about significant figures there. That means really the only number we have there is 3, which has one significant figure. 300, like I wrote, it has one significant figure. If I wrote 300 with a decimal point, it would have 3 significant figures, right? So here we would not want to put the decimal point in this particular case, nor would we want to put anything like 300.0 or anything like that. We would want to leave it as 300. Or you could even do different notation. If you're 3 times, be perfectly fine as well. That's another way, obviously, you could give the answer. Any questions on that one there? All right, so why don't you give it a go here? You go to the local AM/PM, you get a 32 fluid ounce drink of Diet Coke. How many gallons did you drink? I'll give you some conversion factors and some equalities. So take a minute here and see what you come up with. One here, we got 32 fluid ounces. We obviously want to get rid of that. So we do have a path here. We could take fluid ounces to quarts. In this case, obviously, I will use this one as the fluid ounces are on the opposite location. That gives me 32 fluid ounces is 1 quart. When you're doing conversion problems, you have an option. You could lay up an answer at this point, or you could continue on with the calculation. If you do get an answer, maybe not in this case, but if you do get an answer, again, you don't want to round too much until the end, but I'm going to continue on. If I stop the calculation right at this point, the fluid ounces are going to cancel each other out, and we are going to be left with quarts, which is still on top. And that's important because now I know I should use this as my conversion factor. Quarts are on the bottom so that they cancel each other out. That gives me 1 gallon up on top, 4 quarts on the bottom. Quarts will cancel. We're going to multiply across the top, come back and divide by what's on the bottom. And in this particular case, you end up with 0.25 gallons as your answer. Again, you can probably ignore the sig figs there, looking at that one, which is 2 sig figs. The answer, by the way, is not 1/4 because that makes me think you're too lazy to divide. Yes, not necessarily too big of a problem in this one, but I have had people give answers like, 325 miles over 600 hours. Perfect. Right. So don't leave an answer like that. Yeah, divide it out, get a decimal point or whatever it may be. Question on that one there. All right. Let us try another one maybe. Antibiotic dose is 500 milligrams. It's ordered in 250 milligrams and 5 milliliters, how many milliliters would you be given? So I want you to give that a go, see what you come up with. In a doses of 500 milligrams. We want to know how many milliliters would that be. Again, we want to cancel out the milligrams. So we could use really this, which was given to us in the problem, as really like a conversion factor that basically the medicine comes 250 milligrams per 5 milliliters. We would do that here. We would have our 250 milligrams on the bottom, our 5 milliliters there on top. Milligrams would cancel in this case, leaving us with milliliters. We would take 500 times 5 and divide it by 250. I think that's a 10 milliliters would be given. Sig fig wise, this guy's got 3. This is not a true exact equality, right? Because it's specific here for this guy. So we probably would look at the sig figs here as being 2 and probably give something like 2 significant figures in this particular case. Any questions on that one there? Again, that's not sort of a known definition, right? It's sort of specific for this question. And we probably would kind of look at the significant figures in that particular case. Any questions on that there? Yeah. Yeah, so that would be two significant figures. That 0 would then be significant because of the decimal point that's there. Yeah. Questions? All right, we will lay it up there for today.